So taking just a minute to reflect, we're now kind of we're 2/3 of the way through our agenda for this course. So we know about the fields made by stationary charges and how they affect other stationary charges. We know about the fields made by moving charges. Those are magnetic fields, and how they affect other moving charges, magnetic force, which has various interesting applications. We know about fields driving currents in circuits, fields inside capacitors. So we know a lot about patterns of field in space. And I'm saying field here because I mean both kinds, electric and magnetic fields. And you can predict field. We know how to predict the patterns of field in space by using equations to, if we know where the source charges are and how they're moving, then we can use the Coulomb field equation or the Biot-Savart equation to predict the values of electric and magnetic fields at other locations in space. And you've done this with pencil and paper, and you've done it with computers. What we're going to talk about now, sort of reflecting on patterns of field in space, is actually kind of going the other way. So we're going to find that from observing patterns of field in space, so we observed patterns of field in space, and we deduce the source charge distribution that made them. This is actually more useful than it may sound. People who study, for example, plasma physics, which is a big feature of studying stars, can observe magnetic fields coming from stars, but they have no idea where the source charges are that are making these. And so by working from the observed fields, they can guess where charges and currents are in stars, for example. So this actually has has applications. It's also something that physicists like a lot because it's sort of mathematically elegant. And so what we're going to be talking about is Gauss's law, which tells us about one thing about electric and magnetic field distributions, and Ampere's law, which tells us other things. And it's going to involve, the kind of reasoning we're going to do is really very different from what we've done. There's been a lot of sort of algebra and grinding through algebra and calculus. This involves actually looking at the symmetry of situations and drawing conclusions from that. Reasoning from symmetry is an important kind of reasoning in physics, but it will seem mostly very unfamiliar to many of you because you just haven't had much practice doing this. So here's the idea. The game we're going to play is to imagine that we have an imaginary box that we can place somewhere in space. And the box is opaque, but what we can do is we have our little proton on a spring, so we can measure the electric field at all locations on the surface of the box. So let's see what that might look like. Okay. So suppose that we have this opaque box, We've placed it somewhere in space, and we've gotten out our little proton on a spring, and we put it at all these different locations on the box. In this case, it's not a real box because it's a mathematical construct, and it's not affected by fields. It's fairly important that this be not affected by fields. So we will imagine a box. And so we observe this pattern of electric field all over the surface of the box. Now the question is, what we're going to deduce is what's inside the box. So what's inside the box? You have four choices: positive charge, negative charge, zero charge, or you can't tell. Schrodinger's cat is not inside the box. Schrodinger's cat may be inside the box. So we have an overwhelming vote for positive charge inside the box. So this sort of prickly porcupine appearance with fields pointing out suggests that there's going to be positive charge inside the box. We can check this. Let's see if we can show the charges. So we make the box a little bit transparent here, and we see that in fact there are positive charges inside this box, and that is responsible for the field pointing away from the positive charges. Okay, in fact there are three positive charges inside the box. Okay, so actually notice that you were able to deduce from the pattern of field what was inside this box. Okay, fine. So now we go to some other location in space and we deploy our imaginary box, and we measure the electric field all over it. And for this once, we violate our own convention, and we draw the electric field with the point of the vector at the observation location, because if we drew it with the tail at the observation location, the arrows would be inside the box and we couldn't see them. So we go measure the electric field all over the surface of our box here, and we find electric field pointing inward. And so, of course, the question is going to be, what's inside the box? And you say overwhelmingly that there's negative charge inside the box because the electric field points toward negative point charges. And let's check this by showing the charges here. And we see that there are indeed negative charges inside the box, and that's why the field is pointing inside the box. So again, just from observing the pattern of field on the surface of this closed box, we can tell what kind of charge is inside the box. Okay. This is maybe slightly more interesting. So you measure the field at the indicated locations on this box, and you find this pattern of electric field. What's inside the box? Well, it's almost evenly split between positive and zero. Now, if you said 0, you might have been thinking about a dipole, which definitely would have a net charge of 0. But think about the electric field of a dipole. So if there's a dipole inside this box, if the positive charge is on the right, the electric field to the right, on the right side, would definitely point out. But if the negative charge is on the left, the electric field on the left side would be pointing in. So this actually can't be a dipole. It doesn't have the right pattern of field to be a dipole. Now, one thing I didn't make explicit is that the box isn't the only place in the universe where there can be charge. So there could be charge outside the box too. It's just that some of the charge has to be, we're asking not what's all the charge in the universe, but just what's inside the box. So if you think about this distribution in terms of the fact that you could have charge both inside and outside the box, you might want to think about what charge distribution could produce this field, and then what would be inside the box as a result. So let's just try it one more time. Let's think through one more time. What charge distribution could produce a field like this? So this time what you say is there's a big vote for net positive charge. And probably if you were thinking of something, let's show the charges. So what we've got here is basically a charged plate approximated by a whole bunch of point charges. And so a lot of the charge is actually outside of this box, but not all of it. So if we look inside the box, we make the box transparent. We look inside the box, we see that there's a bunch of positive charges inside the box as well. So you correctly decide that there is positive charge inside the box. Okay. How about this one? We measure the electric field all over the box, and we find that no matter where we measure it, it's pointing to the right. What's inside this box? And notice the question is not what's the charge distribution that makes this field. The question is what's inside this box. So mostly you say a net charge of 0. And we can rule out net positive charge because if the charge inside was positive, we know that the electric field would be pointing away from those positive charges, and it isn't always. Likewise, if it was negative, it would always be pointing in. So it points in here, but it doesn't point in here, so it can't be negative. It points out here, but it doesn't point out here, and it doesn't point out on the side, so it can't be either positive or negative. So indeed, it has to be 0. Now, this doesn't tell us exactly what the charge distribution is that made this field, and in fact, there's several possibilities. So here is the one that actually was used to generate this, which is a positively charged plate on the left and a negatively charged plate on the right. So basically we're inside the capacitor near the center. Notice how nice and uniform and parallel the field is. And inside the box, the charge is 0. Can you think of a different charge distribution that would make this pattern of field? Couldn't you have one of either of the plates? Yes, if you're close enough so that we could either have the positive plate on the left, or we could have the negative plate on the right. This is electric field, so it's not a magnet. Where else have we seen so those are good answers, just one plate or the other, but not both. Those are very good answers. Where else have we seen a field that's completely uniform in magnitude and direction through some region? Yes, in a wire in a circuit. So instead of these plates, we could have been inside a circuit where we had rings of a gradient of charge around the surface of the wire. So say positive charge on the left, fading through neutral, and then coming to negative charge on the right. That would also make this pattern of field. But our answer to the question would still be the same. The answer would be, but inside, in the region where we're measuring the field, there is 0 net charge. So let's see if we can actually think about translating our perceptions here, our conclusions, into a mathematical equation where we could really capture this. So one of the things that you were keying off is the direction of the field, right? And the direction of the field relative to the inside of the box, kind of. So if you had the field pointing outward, you said that was probably due to positive charge. If it pointed up, that indicated that there wasn't charge inside the box making that, maybe. If it pointed inward, that looked like negative charge. So the angle is actually important. So we need to quantify this angle. And so there are lots of different ways to measure an angle. The way we choose is to take for one piece of the surface, and here we're talking about just this end piece here of our box, right? So the end surface of our box. Remember that one way to describe a plane is by just giving a unit vector that's normal to the plane. So if we wanted to say the xy plane, we would just give the unit vector 0, 0, 1, because that's a vector normal to that plane. And it's easy to say xy, but if you've got a tilted plane, then life gets very complicated in terms of words. So giving a unit vector perpendicular to something. So what we're going to do is we're going to take the unit vector that's perpendicular to this piece of the surface. It's conventionally called n hat. And we're going to measure, we were interested in the angle between the electric field and this unit vector. And there still could be two unit vectors perpendicular to the surface, right? There's one going out and there's one going in. We picked the outward going normal. And then we're interested in this angle, and we want some quantity that's positive when these vectors are in the same direction. And we want it still to be positive there. We'd like it to be 0 here. And we'd like this to be negative here because the charge was negative if the vector pointed in. And so that looks like a cosine of that angle. So we're interested in the cosine of the angle between the electric field at this location, we measured it, and the unit vector that's we're going to call n hat, that's normal to that piece of the surface. And so n hat is called the unit normal vector. And so cosine of 0 degrees is 1, cosine of 90 degrees is 0, which is good, and cosine of 180 degrees is -1, so that seems like a good idea. But something we haven't talked about yet is the magnitude of the electric field. So think about this. Here's our box, and we measure the electric field all over it, and it looks like this, and we say good, positive charge inside and whatnot. And then we come back later, we move our box to some other location, and we get this. We haven't changed the box, and the field is in exactly the same directions, but the field is bigger. So it looks like we also need the magnitude of the field here. So let's record this in our notes. So we have our box here. And we have our unit vector normal to a piece of the surface that we're going to call n hat. And if we measure electric field here, we want that to come out to a positive number, and it should be bigger if the magnitude of the field is bigger. That should be 0, and that should be a negative number, and it should be bigger if the field is bigger. And that actually looks like a dot product. So remember that the vector, the dot product of E and the unit vector n hat, we'll take into account, so the magnitude of this is the magnitude of E times 1 times cosine of theta, where theta is the angle between E and the outward going normal. And if they're both out, so if we have E and n hat, we'd get E dot n hat is going to be our vector, which is some E00 dot 100, and that's going to give us just the magnitude of E, and it's going to be a positive number. If there's a right angle, then we'd get E dot n hat is going to be 0 E0 dot 100, and that's 0. And if E is opposite, so E is going in and n hat is going out, then we'd have E dot n hat would be minus E 0 dot 100, and that would give us a minus E. And so so that comes out right, and it takes into account both the magnitude of E and the angle between E and n hat. Okay. But since we're worried about magnitude, we need to worry about another thing, which is how big our box is. And so let's go back to our program here. So we're in some location in space. We have this box. We measure the electric field all over it. And we're going to add up all the E dot n hats on this surface and the E dot n hats on that surface and the E dot n hats on that surface. So we're gonna calculate this quantity on every surface or every piece of a surface and add them all up. So basically what we're doing is it's called a surface integral because we're summing over something all over the surface. But what if we had been in exactly the same location, but we just used a bigger box? We would have gotten much smaller field measurements. So in order to get some sort of accurate measure of the magnitude, our answer has to be independent of the size of our box. And what that means is we have to take the surface area of our box into account. So if we multiply this large value of E dot n hat times the small surface area, we want to get the same result as if we multiply this small value magnitude of E times n hat by this much larger surface area. So we've got to take into account the surface area. And so one clear way to do that is just to make sure that we multiply by the surface area. So we need to take surface area into account. And so we can actually multiply by the area. Now, we have to be a little careful when we're doing that, because suppose we have a piece of a surface here, and at this location, we have an electric field going this way, but at this location, we've got an electric field going this way. Now, n hat is still the same in both cases, but we're going to get a different E dot n hat. So of course, what we're going to need to do if the electric field isn't uniform over a surface is we're going to have to break this surface into little pieces and make these measurements for every little piece, add them all up. And so we're going to call the area of a piece delta A. So because it's a small piece of an area. And so what we've ended up defining is a quantity called electric flux. And it's measured on a surface. So how do we do for a sphere? We get to a sphere in a minute. And so the definition of electric flux is going to be, we have our dot product of E dot n hat, and that gives us the magnitude of E and the cosine of the angle. We're going to multiply by each little piece delta A that we measured it on, and then we're going to sum all over the surface. And this thing, there's a symbol used for it. We use the Greek letter phi because phi sort of sounds like flux. even though it really should be pronounced phi, which, well, I guess that sort of sounds like flux. So this is the electric flux. And what are its units? Well, we have volts per meter. The unit vector doesn't have any units. Area has meters squared. So it looks like the units are volts times meters. And what our goal is going to be is to relate the electric flux mathematically on a closed box to the amount of charge inside it. So that's the game we're going to play. Now notice that if we get the flux on one surface, like one piece of a surface that's just not a closed surface, it really doesn't tell us anything. We have to be able to do it, but what we're going to want to do is add up the flux over every piece of that closed surface, which could be a sphere. And then that should be related to the amount of charge inside. So let's see if we can actually calculate flux on one piece of a surface. So here's our question. So this is whoops. Oh, that's all right, actually. We have a rectangular surface here. The electric field on all over this piece of, all over the surface, it's uniform on this surface, okay, is negative 230, 370, 0 volts per meter. N hat is in the plus y direction. So what is the electric flux on this surface? Okay, you are going to actually have to be able to do this, so it would be a good idea to do it now. So most people said 2.888 volt meters, which is correct. But it was only 46%. So let's just work it out real quickly. We have the electric flux, whoops. The electric flux is going to be the sum over this little piece of the surface of E dot n hat times delta A. Now, since the field is uniform on this surface, we can just use the entire area of this. So it's going to be equal to minus 230,3700 volts per meter dot 010 times the surface area, which is 0.06 meters times 0.04 meters. This is the area. And we do indeed get 0.888 volt meters. Okay, let's try one more. So here we have a disc-shaped surface, and let's write our equation here again. So electric flux is sum of E dot n hat delta A. And remember that the dot product can be evaluated two ways, right? So the question is, what is the electric flux on this surface? All right. So the majority say 5, which is 1.54 volt meters, and that is not correct. So let's see why it's not. So a little thought is required here, because when we're evaluating E dot n hat, we have to think about what n hat really is. And so n hat is going to be the unit vector perpendicular to the surface. And so this is n hat. And so this angle theta that we've been given here is not the angle we need. So the angle we need is not theta. We need this angle. It's not the angle we need in the dot product. So this is going to be 90 minus theta, the way theta was specified here, right? So what we want for the electric flux is going to be equal to 600 volts per meter. And here we're going to use the magnitude of E, magnitude of n hat, cosine theta formulation, times the cosine of 90 minus 25 degrees, times the area, which is pi times 0.03 meters quantity squared. And what we end up with is a 0.717 voltmeters. So you need to think about the meaning of these things before we do them. Now, basically, what we're doing in this dot product, and it's easy to see when you work out the dot product using with the full vector formalism, is that we're actually taking the component of E that's perpendicular to the surface. Okay, so we end up with, because minus 230 times 0 is 0, so the only thing that contributes is the component of E that's perpendicular to the surface here. So one way to think about this is that we're, if we have some little area delta A and we've got some electric field E here, that we're taking essentially E perpendicular. Okay, so what we've really got is the perpendicular component of E here. Guess I made that slightly too long. A different way of thinking about it is actually, which is sometimes useful, is that we're taking the component of the surface area that's perpendicular to E. So if we have E this way, this is actually equivalent to projecting this surface onto a plane perpendicular to E. So it's sort of, we're thinking of a projection of the delta A perpendicular. Not always all that useful, but so, well, let's see. Let's try to draw it so it actually looks perpendicular. So delta A perpendicular to E might look something like this. And so component of E perpendicular to surface, or component of surface perpendicular to E. Okay, so what we want to do here is we want to, so if we're going to add up the flux, this flux by doing a sum or a surface integral, we have what we want is to get the electric flux on a closed surface has to be equal to something related to the charge inside. Something related to, okay. And so what we need to do is we need to be able to add up the flux on a closed surface and then equate it to the amount of charge inside. So let's start by adding up the flux on a closed surface, and then we'll set it equal to, we'll see what we're going to do to set it equal to something. So here's a question of what's the net electric flux on this box. And what we need to do is add up the flux on every piece of the surface and then sum those. So what we're going to get here is the electric flux is equal to the flux on the left sub end plus the flux on the right end plus the flux on the top plus the flux on the front plus the flux on the back plus the flux on the bottom. Okay. Now some of these things we can actually just do by inspection. So what are the easy ones? Well, the first thing we need to do is we need to draw, need to draw n hat everywhere. There we go. So n hat is going to be perpendicular to each face. And then we can see that on the top, for example, E is actually perpendicular to n hat. That's a right angle. So by inspection, we can see that that's 0 because E is perpendicular to n hat. And that's also true on the front, and it's going to be true on the back, and it's going to be true on the bottom. So because E is perpendicular to n hat. So we really only have to do a little arithmetic on the front, on the left and right faces. So the flux on the left face is going to be 400 volts per meter times the cosine of 180 degrees, because the field is going in, but n hat is going out, times 0.03 meters times 0.02 meters, the surface area of this end cap here. And so that comes out to negative 0.24 volt meters. The flux on the right side is going to be 1,000 volts per meter times cosine of 0 degrees times 0.03 meters times 0.02 meters. And that's going to give us a plus 0.6 volt meters. And so the net flux is going to be equal to a minus 0.24 plus 0.6 plus 0 plus 0 plus 0. And so we get a 0.36 volt meters. So we know how to add up flux on a closed surface, but now what we need to do is figure out how that's related to the amount of charge inside. So here's what Gauss's law says. It says that the sum over a closed surface. What does a closed surface mean? It means something that has an interior and an exterior, right? So it's like our box. It's got an inside and an outside, whereas one piece doesn't have an inside and an outside. Of the electric flux is equal to the sum of the charge inside the surface times some constant which turns out to be 1 over epsilon 0. And we need to prove this. So what do we need to prove? One, we need to prove that constant is really 1 over epsilon 0. We need to prove that the size and shape of the surface don't matter. We need to prove that it's true for any number of charges inside. And we need to prove that charges outside that contribute 0 to our sum. So the first thing is to determine that the constant is in fact 1 over epsilon 0. So let's write this as the sum on a closed surface of E dot n hat delta A is equal to some constant K times the amount of charge inside. The simple thing to do is to do this for a point charge. Because we know the electric field of a point charge. So if we put a point charge here, and the surface we'd like to draw around the point charge is actually a sphere, which comes back to Alexander's question. So let's make our surface a sphere. I'm going to draw it in cross section because I can't draw spheres. Okay, so that's a sphere, spherical box. And the electric field, of course, is going to look like this on our sphere. And that looks like it's going to be really tough to add up. However, this is one of these integrals that you can actually do by inspection. Why can you do this by inspection? Because if we have a sphere and we take a little tiny surface area here and we think about here's n hat and here's E, and then we take a different little piece of surface area here. So here's E and here's n hat. We can see actually by the symmetry of the situation that E is parallel to n hat everywhere. So this sum of E dot n hat delta A, we can write as the integral of E dot n hat dA if we make these pieces small enough. And the integral usually has a circle around it to indicate that it's a closed surface here. And I'm not going to ask you to do surface integrals except the ones that you can just look at and see the answer. So, in fact, this actually just the electric flux is E dot n hat dA, and that's just the magnitude of E times the cosine of 0 degrees for every little piece times the sum of all these delta A's, which is E times 1 times, well, what's the surface area of a sphere? So it's 4 pi r squared. But we also know the magnitude of E. So E is 1 over 4 pi epsilon 0 q over r squared times 4 pi r squared, which is equal to q over epsilon 0. So it works for a point charge, and we've proven by and because of superposition, it's going to work for any number of point charges. Would this work for a negative charge? Sure, because the cosine of 180 degrees, everything's going to be pointing in. It's going to be -1, so we're going to get a minus number there too, and it doesn't matter. So we proved our first thing that we have to prove. The size and shape don't matter. Well, this is not a general proof, but you can see that it's true. If we take, so we took a sphere around a point charge here. If we make our sphere bigger, so this is R1 and that's R2. Well, area of 1 is 4 pi R1 squared, and E is going to be 1 over 4 pi epsilon 0 q over R1 squared. A2 is 4 pi R2 squared, but the electric field is smaller. It's 1 over 4 pi epsilon 0 q over R2 squared. And you can see that the area goes up by r squared, the field goes down by r squared, and they cancel out, so the size doesn't matter. Now, what I'd like to show you for fields outside not mattering is another VPython program. What we're doing here is we can drag, this is a program called Fields, which is in the set of demo programs at glowscript.org. And what we can do is drag a charge onto the screen, and then we can actually draw a surface around it and look at and actually visualize the flux. Now, this particular charge is actually, you have to imagine it being a long charged rod that's going in and out of the screen. And when we draw a circle around it, what we're drawing is a cylinder, a cylindrical surface like an oatmeal box, okay? Okay, so here's our charge. And it's a long rod into and out of the screen. And what we're going to do is just draw a surface around it. And as we draw this surface, so we're drawing an oatmeal box around it, basically. Cylinder. So the orange arrow is the electric field, and this yellow fuzz represents the flux, which is positive because it's pointing out. And when we make a closed surface, then it can, what the program's doing is just adding up all that flux and then dividing by epsilon 0 and saying charge is 1 in some units or other. And you can see that it doesn't matter where the charge is, okay? So we get a lot of flux in some places and a little bit of flux in other places. But it still adds up to 1, whereas if we take the charge outside, then it comes to, then it's different. Now, if we put a negative charge inside too, even though the electric field is not zero on the surface and we have a lot of positive flux near the positive charge, we have a lot of negative flux near the negative charge, and so it manages to add up to zero. And if we just have a negative charge, then we only have flux pointing in, and it's still giving us a -1. Okay, so what happens if we have a charge here and we're adding up the flux, but then we have another charge outside? The superposition principle tells us that the net field everywhere on that surface is actually going to be equal to the sum of both fields. And in fact, a charge outside certainly does change the flux distribution on this, on our cylinder. But it's still saying that the charge inside is 1, not 2. How does that work? Well, let's take this inner charge out. And now it's saying that there's 0 charge inside. And the reason that works is that close to the charge, there's a lot of negative flux. But there's a lot of surface area that's not close to the charge. And there's positive flux. And even though it's smaller, the surface area of the sphere that has that positive flux is bigger. And so it actually adds up to a total of a contribution of 0 to the net flux. And this would work for a negative charge too. So if we have a negative charge outside, we're going to get positive flux near this negative charge, but we're going to get negative flux on the regions of our surface that are far from the charge. And so in the end, the contribution of charges outside are 0. So this is a program you can experiment with if you want to. And again, if we add another charge, so we make a dipole inside, it correctly concludes that the net charge is 0 inside because the positive flux and the negative flux add up to 0. Okay, so there's a more formal proof of various of these things in the textbook that you can read if you want. So, but we've basically established that Gauss's law relates the electric flux, so the sum of E dot n hat delta A on a closed surface to the amount of charge inside the surface divided by epsilon 0. And it's usually written as a surface integral because that just means we're taking all our little pieces to be very small. We're not going to ask you to do weird integrals. The only time you're going to be integrating is like we did on the sphere, where it's just clear that you're going to E dot n hat is uniform, and therefore you can just multiply by the surface area. And we'll practice with this a little bit. Now, there's a version of this for magnetism. That has to do with magnetic fields. So suppose we had a box, like our box, and we measured magnetic field all over it with a Hall effect probe or whatever. So suppose we got that measurement. What would be inside the box? Well, magnets are dipoles, right? So what does the pattern of field around a magnet look like? We have field coming So what would be inside here would be a North Pole. And you would get a Nobel Prize if you found this, because as far as we know, it's impossible. So as far as we know, that magnetic fields are always made by dipoles. And there are no North Poles and South Poles all by themselves. And so what Gauss's law for magnetism tells us is that actually that we can't see a pattern of field like this. There are no magnetic monopoles. And so Gauss's law for magnetism would tell us that the net magnetic flux on a closed surface has to equal 0, because there have to be both north and south poles making a. Well, it would have to be a point magnet. Okay, so it would have to be, if you'd have to think of a magnet that's a point north pole, if that's what it was. So it would have to be just a little teeny N in there. Now, there's actually nothing that rules out on theoretical grounds the existence of magnetic monopoles. It's just that we haven't found any. And so as far as we know, they don't exist. So there are a lot of labs that have an experiment off in the corner just kind of running and waiting to see if a magnetic monopole might happen to pass by their experiment, but no one's really found one yet. So as far as we know, they don't exist. So what's important? What's the takeaway message here from this lecture? No, electromagnets are dipoles. Electromagnets are actually just loops. So an electromagnet is just a coil with current running through it that may have a piece of iron in the middle, so that the magnetic field inside the loop actually magnetizes the iron. But remember, we still have these atomic dipoles in the iron, or it's all these little atomic dipole moments that are aligning up to make a magnetic field there, and the loop is a current loop that's a dipole. So electromagnets are dipoles.